Back. Today, we are going to crack a classic calculus problem. Now, this one looks deceptively simple, but trust me, it holds the key to a really powerful technique. So get ready, because we're about to dive deep into the world of implicit differentiation.
Okay, so here's our challenge for today. We need to find y prime, the derivative of y with respect to x for this equation right here. Y squared plus x squared equals 25.
Now, before your brain gets tied in a knot looking at that, let's just take a step back and remember what this actually is, right? This isn't some abstract monster of an equation. It's just a circle, a simple circle, centered right at the origin with a radius of 5. We can actually picture this thing.
So here's the puzzle. Normally, what would we do? We try to get y all by itself on one side, right? And then take the derivative. But if you try that here, well, you end up with a messy plus or minus square root. And that's just not clean. You just know there has to be a more elegant way to do this. And guess what? There is.
So, yeah, this problem calls for a whole new approach. It's time to pull out a secret weapon from our calculus toolkit, one that's designed for exactly this kind of situation.
And that weapon, it's called implicit differentiation. Honestly, the name kind of says it all. We use it when y is all mixed up, or implicitly defined, inside the equation, instead of being nicely solved for on one side. And this is the big mind shift right here. You have to forget about trying to isolate y first. Instead, we're going to treat the entire equation as one single thing, and we're going to hit the whole thing, both sides, with the derivative operator, all at once.
Okay, so theory is great and all, but let's actually see this thing in action, right? Let's break down the solution into 3 super clear, manageable steps so you can see exactly how it's done.
So here's the game plan. Step 1, we differentiate both sides of the equation with respect to x. Step 2, and this is the really important part, we have to apply the chain rule to any term that has a y in it. And then step 3 is the easy part. Just do a little algebra to get y prime all by itself. Ready? Let's do it.
All right, step 1, super simple. All we're doing here is formally writing it out. We're going to take the derivative with respect to x, that's what d dx means, of the left side, and do the exact same thing to the right side. We've got to treat both sides equally.
Okay, now this is where the magic happens. Let's take it piece by piece. The derivative of x squared? Easy, that's just 2x. The derivative of the constant? 25? Even easier, that's just 0. But that y squared term, that's the special one. See, we have to remember that y is really some function of x, so we have to use the chain rule. The derivative of the outside is 2y, but then we have to multiply it by the derivative of the inside, and the derivative of y is just y prime. This step right here is the absolute heart of implicit differentiation.
And just like that, we're on the home stretch. The calculus is done. Now it's just algebra. Our goal is to get that y prime term all alone. So, first move, let's just subtract that 2x from both sides of the equation. See, the hardest part is totally behind us.
All right, we followed the steps, we did the hard calculus part, and now it is time for the payoff. We've got our answer, but what's even more important is understanding what this answer means.
And here it is. All we do is divide both sides by 2y, the 2's cancel out, and we're left with this beautifully simple result, y prime equals negative x divided by y. Look at that. All that work, and it boils down to such an elegant little formula. So, that's the answer. But so what? What does this formula actually tell us? What does negative x over y even mean when we're talking about our circle? Let's connect this algebra back to the geometry. And this is what's so cool about it. This little formula, it's the recipe for the slope of the tangent line at any point. Literally any x, y point on that circle. You just pick a point on the circle, plug its x and y values into the formula, and boom, you've got the slope right there. No need to solve for y first. This technique is incredibly powerful, and it works for all sorts of crazy curves, even ones that aren't technically functions. So I'm going to leave you with a final question to chew on. You now have the master formula for the slope anywhere on this circle. So, where on the circle would the tangent line be perfectly vertical? Think about our formula. Y prime equals negative x over y. What would have to be true about that fraction for the slope to be vertical or undefined? Give it some thought, and you'll